Hi, my name is Sep Ching Chin. I'm the leader of this group here, and my matrix number is AA240585, and I'm from Group 1.
Good morning, everyone. My name is Lee Xing Ying, and my matrix number is AA240900.
Morning, everyone. My name is Eng Han, and my matrix number is AA240536.
Assalamualaikum and good morning. My name is Muhammad Danish Hanin bin Hadzesha and my matrix number is 240571.
Here comes to the test 1. Production output in an assembly line. A mechanical assembly line begins by producing 100 units in the first hour and increases its output by 15 units each subsequent hour. Question 1. Determine the numbers of units produced in each of the line 5 hours. So for the question, we have facts here. The assembly line produced 100 units in the first hour. And the second point of the facts is output increased by 15 units each subsequent hour. Idea is using the formula arithmetic sequence, which is an equals to a plus n minus 1 times d. Here comes the next one, learning issue, which is how to apply arithmetic progression to calculate outputs over time. The action plan will be using formula arithmetic sequence and calculate the production for hour 1 through hour 5. It will show that the result of hour 5 is 160 units. Next will be our test 1 question to calculate the total production over the first 5 hours. The fact is production over 5 hours follow an arithmetic progression which is 100, 115, 130, 145, and 160. The idea is using our arithmetic series sum formula, which is Sn is same as n over 2 times 2a plus n minus 1d, where a is 100, d is 15, and n is 5. Down to the next one, which is learning issue. How can arithmetic series formula simplify summing production output over time? The action plan will be apply the arithmetic series formula S equals to 5 over 2 and then times 2 times 100 plus 4 times 15 equals to 650. And to verify it, we plus everything with using the formula just now will be 650. So the formula works. Question 3. Discuss how understanding production rates can impact efficiency and resources allocation in a manufacturing setting. The facts is the production rate impacts material use, labor allocation, and machine efficiency. Fluctuation or consistent increase in production rate require careful planning. This comes to the ideas, which is we need efficiency improvement. Monitoring production rates can identify bottlenecks or efficiency in the process. Well, next will be resource optimization, which is understanding rates ensure timely procurement of material and proper labor scheduling. Down to the learning issue, what strategies can be implemented to align resources availability with production trends? Action plan will be develop contingency plans for handling production rate changes such as additional shift or alternative suppliers for raw material. Thank you.
And for the question 1, the production hour line starts at 125 units per hour, and the hourly output increases by a factor of each hour. Because of this, we can use the formula for the nth term of a geometric sequence, which is a sub n equals a times r to the power of n minus 1, where a equals 125 and r equals 2. So from that, we gotta know how to use the geometric sequence to calculate outputs over time. And to that I say, we use the geometric sequence to calculate the production for the 6th hour, which we replace the words with a sub 6 equals 125 times 2 with the power of 6 minus 1. And the calculation we will get a sub 6 equals 4000 units. And we have completed the question 1. Question 2 is to find the total production for the first 6 hours. Because we have discovered the production for the first, the following production for the second, third, fourth, and fifth are not necessary to find, as the total production for the first 6 hours can be calculated without it. As there is not an order of production line given, we can use the sum of a geometric sequence, which is S sub n equals a times r to the power of n minus 1 divided by r minus 1, and r is not equal to 1, where a equals 125 and r equals 2. So how does geometric series formula simplifies the total output production over time? As to that, we use the formula to calculate the total production of the first 6 hours, which is S sub 6 equals 125 times 2 to the power of 6 minus 1 divided by 2 minus 1, which will be 7,875 units. And we have completed the task for question 2. And for the last one, question 3, the question is, if quality control can inspect 1000 units per hour, in which hour will inspection capacity first be exceeded? So from the question, the production output starts at 125 units per hour and increases exponentially. And the other point is, the identified inspection capacity is 1000 units per hour, which must be exceeded to complete the task. So we must compare with inspection capacity with also including the geometric sequence formula, which a sub n is more than 1000. A sub n equals a times r to the power of n minus 1. The initial production output for a is 125 and the common ratio r equals 2. So how does this solution guarantee us to identify the specific time the moment the production output exceeded the inspection capacity? So here is the calculation proof, which we replace the words with the numbers, where 125 times 2 to the power of n minus 1 is more than 1000. And as we simplify the equation and solutions, we will get n is more than 4. Thus, n will equal to 5, which is the hour where inspection capacity was exceeded. And that is the final answer for the question 2. And that's the end for test 2. Thank you.
For test 3, question 1, calculate the size of the fourth part if the size of the first part is 10 units. Facts of this question is, each part of a mechanical system is determined by a geometrical sequence. Each part is 1.5 larger than the previous part. So the idea for this question is, the size of each part follows the formula Tn equals AR power negative minus 1. The learning issue of this question is, how can we get the size of each part of the mechanical system by using a geometric sequence? Action plan of this question is each part is 1.5 times larger than previous, so R equals to 1.5. Size of the first part is 10 units, so A equals to 10. We can use the formula Tn equals to AR power n minus 1 to get T4 equals to 10 times 1.5 power 4 minus 1 equals to 3,375. For question 2, a machine processes parts with a speed that increases by 5 units each hour, starting at 20 units per hour. What are the processing speeds of the first 4 hours? The fact of this question is the speed of the mechanical system increased by 5 units each hour. The machine starts working at 2 units per hour. The idea for this question is the processing speed of the first 4 hours can be calculated by using the formula Sn equals to A times A power of n minus 1 per R minus 1. The learning issue of this question is, how can we get the processing speed of the mechanical system by using a geometric sequence? Action plan of this question is the speed of the mechanical system decreases by 5 units each hour, so R equals to 5. The machine starts working at 20 units per hour, A equals to 20. So we can get S4 equals to 20 times 5 power 4 minus 1 per 4 minus 1 equals to 4,160.
For question 3, calculate the total distance covered by a machine moving with a constant increase in speed of 2 ampere square for the first 10 seconds. What type of sequence represents the distance covered? The fact involves a machine accelerates at 2 ampere square over 10 seconds. The total distance traveled can be calculated using this formula S equal to 1/2 AT square, which gives us a total distance of 100 meters. The idea here is to recognize that the distance covered each second follow an arithmetic pattern. The learning issue is understanding how motion equations and arithmetic sequences apply to real-world machines. Our action plan involves studying motion equations, analyzing patterns, and applying this to similar systems. Next, for question 4, discuss how understanding sequences and series can impact the design and functionality of mechanical systems. The fact highlights the importance of sequence and series in mechanical design. Whether it's scaling part sizes, analyzing motion, or planning system performance, understanding these patterns is crucial. The idea is that sequences help optimize designs, cost, and performance. The learning issue is understanding how sequences impact mechanical engineering practically. And the last one, our action plan, is to explore case studies that demonstrate the application of sequences and series in areas like scalability, production efficiency, and system analysis. That's all from us today. Thank you.